Dr. Alexander EISFELD is an independent group leader at the Max Planck Institute for the Physics of Complex Systems, holding a Heisenberg Fellowship of the DFG. Dr. EISFELD received his PhD in physics in 2006 from the University of Freiburg, Germany. His main research interests are collecting effects and quantum transport in atomic, molecular, and nanoscale many-body systems. Examples are photosynthetic light harvesting systems, aggregates of organic dyes, assemblies of ultra-cold Rydberg atoms, or photonic systems. To handle these typically large and complex systems, he uses a variety of approaches, which include molecular dynamic simulations, quantum chemistry methods, non-adiabatic quantum dynamics, and open quantum system formalisms. One particular research interest is solving non-Markovian open quantum system dynamics using efficient stochastic Schrodinger equations. On behalf of all the members of ROWS, I welcome you, sir, to this webinar. And I also welcome all the invited guests and participants to the webinar. A humble request to all the participants, all are requested to keep your microphones muted till the end of the webinar. After the talk, time will be given for the interaction with the speaker, and also please take care not to present your screen in between. Link for generating e-certificates and providing feedback will be given at the end of the webinar. Now, I kindly request Dr. Alexander EISFELD to begin the presentation. Sir, please.
First of all, I would like to thank you for your nice introduction, and I would like to thank the organizers for giving me the opportunity to present something at this very nice conference. And yeah, so I will talk about near-field spectroscopy of molecular aggregates, and I'm a theoretician, as you have heard in the introduction, but I will try not to have too complicated theory here, but I will convey the basic principles of the systems, and I will actually present also some experimental work of collaborators. And the outline of my talk is at the beginning. I will give you a brief overview of what we do in my group, so that you can see what is the global theme in which this research is embedded. After that, I will give an introduction to molecular aggregates, where I give some basic effects and the basic theory that is required. And I will try really to stay rather simple. After that, I will discuss an experiment that's a superradiance of a PDCDA molecule, actually of many PDCDA molecules that are placed on a dielectric surface. And that also motivates then why we would like to use near-field spectroscopy to investigate such systems. And I will conclude with a summary and a short outlook. But the main focus of my work is the dynamics of complex quantum systems. And there, as you have heard, we are mainly interested in collective effects that appear when many individual systems form a new, larger system. And a main interest is how does such collective system interact with some light. The light is either used to probe the system or to steer something. And typically, the systems we look at, electronic excitation or electronic motion is coupled to some nuclear degrees of freedom. And this altogether results in an interplay of coherent evolution, some dissipation, and typically we have this external driving. And we look at various types of systems, for example, coupled cavity systems or nonlinear dynamics in this type of shuttles or coupled waveguides that you drive strongly. Then a large part of my work is about highly excited Rydberg atoms, where we try to get entangled states and use them for quantum simulation and quantum computing. Then today I will talk about molecular aggregates and about this near-field spectroscopy. There we also do a lot of femtosecond pump probe investigations. And a large part of my work is actually concerned with quantum simulators for open quantum system dynamics. For example, using Rydberg atoms, we have also proposals how to use superconducting qubits. And recently, we did calculations on this IBM quantum computer. And for all this work, typically, we use some kind of machine learning techniques, for example, Gaussian process regression, to get information about molecular conformations from spectroscopy, or you will see in this talk, neural networks to get to solve inverse problems. So let's start with the actual talk, and we start with what are molecular aggregates. And here you see three prominent examples. One are the light harvesting systems in photosynthesis, and here organic dyes that self-assemble in solution. And here the topic of today's talk, molecules on surfaces. So this will be the main topic. And in all these three cases, there are the molecules that form the aggregate. For example, here, these are bacterial chlorophyll molecules arranged here. This thing consists of hundreds of thousands of individual organic dye molecules, and here also hundreds of molecules are participating. And the important thing to remember is that the molecules here, they are so far apart that there's no overlap of their electronic wave functions. So each molecule really stays as an individual, and no electrons tunnel and no chemical bonds are between these molecules. However, there's a strong interaction between the individual transition dipoles of these molecules. And this interaction, you can think about, comes from the fact that the molecules have a large transition dipole between their ground state and their first excited state. So in the rest of the talk, when I talk about a molecule, I essentially only consider the electronic ground state of the molecule and the first electronically excited state, and I abbreviate them with G and E. And the transition dipole between these molecules, that I denote by a mu. And for those who have forgotten, the transition dipole is that quantity that interacts with electromagnetic radiation. So mu times the electric field gives you the strength of absorption or emission. And this transition dipole, in the case of molecules, is you can think of as being a vector that is fixed with respect to the molecular structure. For example, here for these PDCGA molecules that we discuss later, the transition dipole points along this axis and has a value of 7 dBi roughly. And so this actually, there's a transition density, but to a very good approximation, you can replace this complete transition density simply by a point dipole. And the interaction between these dipoles, you can now visualize as follows. Let's look at the situation where initially molecule 1 is excited, and molecule 2 is in the ground state. So it's a situation that I sketched by E, first molecule excited, second in G. Now, there can be a downward transition of molecule 1 via this dipole, and simultaneously, this is excited via the dipole, so radiation essentially is transferred from here to here. And this can swap this EG to a GE. Now molecule 2 is excited, molecule 1 is in the ground state. Of course, this can go back and forth. And the interaction that is associated with the coupling between EG and GE is simply the interaction of these transition dipoles. And it has the form as a standard dipole-dipole interaction. It depends on the relative orientation of the two dipoles, on the orientation of the dipoles with respect to a vector that connects the two centers, and it depends 1 over distance cubed on this distance. So it's the standard dipole-dipole formula. And besides the the possibility of transferring an excitation from one molecule to the other. Of course, this interaction also modifies the eigenstates. And this is shown here. So if you have two molecules, then the degenerate states EG and GE, they split by the interaction. So they form new states. And these are simply coherent superpositions of EG and GE. One is an in-phase superposition and the other an out-of-phase. And the splitting is given by 2 times the interaction strength. In the case when you have more molecules, so of course, if you have one molecule, it can also be in the ground state, or both molecules could be in the excited state. So we would have this. If we have more molecules, then we still can have the situation that all molecules are in the ground state, or we can have the situation where one molecule is excited and all the others are in the ground state, and then the eigenstates would be superpositions of states where a single excitation is in, or we can have states where more than one excitation is in the system. And you can really classify this because the energy gap between the ground and the excited state is much, much smaller than any interaction between molecules. So really these bands are formed, and we will be mostly interested in this band where we have altogether one excitation in the system. And I will sometimes refer to that as the one exciton band or the one exciton manifold. And these eigenstates and the corresponding eigenenergies, they depend on the position and the orientation of the molecules. So this is the main thing you should keep in mind. Okay, so this interaction we have seen, that can lead to a transport of the excitation. That is, of course, very important in photosynthesis, where you absorb the energy and then you transport it along these molecules to reaction centers where the charge separation takes place. For practical applications of these dyes, actually, it's also interesting that there are new optical properties emerging. And this has led to many applications. For example, the classical application is as synthesizers for color photography. That was actually where they were discovered nearly 80 years ago. Then they are used as light-emitting materials for contrast imaging, as colorants in food. They are used to measure membrane potentials in vivo, for organic solar voltaics, and we suggested them to use solar light collectors. And although these aggregates are investigated for over 80 years now, there are still many open questions. For example, can one infer the arrangement from the optical properties? Or can one tailor the optical properties by changing the arrangement? And how can one achieve efficient energy transport? How do they actually interact if you place other nano-objects close by? And the main problem from the theoretical side is that you're dealing with many molecules, and each molecule, of course, has many nuclear degrees of freedom, and typically also there's a surrounding which you couple, and that cannot be neglected. And sometimes it must be modeled in rather detail, for example, in these light harvesting systems. And in the following, I will no longer focus on transport, but only on the optical properties. And traditionally, these molecular aggregates are investigated in solution, for example, in water at room temperature. And this is also what you see here. These are experimental spectra of 2 different molecules in water at room temperature with a very low concentration of the molecules, so that you have spectra of essentially individual molecules. And this is what you see here. And you see these spectra, they cover a broad range of the visible spectrum. And both show a more or less pronounced vibrational structure. For example, here you see it quite well. This is a high energy vibration of the molecule, and this is the corresponding vibronic progression. Now, if we look at fluorescence, so emission, then both show also a broad emission, which is essentially a mirror image of the absorption spectrum. This is typical, and it shows that essentially the ground state potential and the excited state for an Oppenheimer surface, they have the same harmonic shape. If you now increase the concentration of the dyes, then for this dye, suddenly there appears this spectrum, so this red curve here. And you see, the spectrum is redshifted, very narrow. You don't see any vibrational progression anymore, and you have a very strong absorption here. This is called a J aggregate or J band. And also the emission is essentially a single peak sitting exactly at the position of the absorption. In this case, you get the blue shifted spectrum, and there's no emission at all. So the emission is completely quenched. So, and of course, the question is, why do different dyes have such different spectra? And to get a basic understanding for this, which is also helpful later for the talk, we look at simple examples. So simple numerical calculations. The first, a little bit theory, how we model these systems. So the basic Hamiltonian that I will use, I will call it the aggregate Hamiltonian, consists of the Hamiltonians of the individual molecules, and there's this dipole-dipole interaction between molecule N and M. And to model the optical properties, absorption and emission, we need the transition dipole operator of this complete assembly of molecules. And this is simply given by the sum of the individual dipole operators. So as we have seen before, the electron ground state, which I call G aggregate, will be simply the product where all the molecules are in their ground state. And we're interested in states with one electronic excitation, as I said before. In these states, I abbreviate with N, and N means that the nth molecule is excited, the others are in the ground state. Then in this one exciton manifold, the Hamiltonian can be written like this. So on the diagonal are the transition energies. So this is the energy difference between the ground state and the excited state. And on the off diagonal are the couplings, so these dipole couplings that can transfer excitation from N to molecule M. For spectroscopy, it's more convenient to have these eigenenergies and eigenstates. So they are obtained by diagonalizing this Hamiltonian. And as we've seen before, they typically form a band that is well separated from this ground state. And these eigenstates can be written as a superposition of these localized excitations. And these expansion coefficients I will denote by Cn, and L labels the eigenstate. For example, here, this is an eigenstate which have L equal 1, this would have L 2, and so forth. And this will become also important later. Okay, and then the transition strength from the ground state to one of these excited states L is, of course, then simply given by the matrix element of the ground state wave function, and the corresponding excited state L, and you take the complete dipole operator. And then you take, after that, the absolute and the square. And if you plug this in, you see that the absorption strength is a sum of these individual transition dipoles, they are vectors, weighted by these coefficients. And then you do this absolute square. So this can become 0 because phases can cancel out. Okay, let's now look at a few very simple examples so that you get a feeling how things actually can happen. So we look at a long linear chain of identical molecules, as I have sketched here. And for simplicity, I look only at interaction between nearest neighbors. So you have this very simple Hamiltonian that you can solve analytically. And one sees that for such a situation, so all the molecules are parallel, then only one state absorbs, and the absorption strength to these different states is given by this formula. So the state that will have the label 0 now here, that absorbs, and it carries n times the absorption strength of an individual molecule. And the state is located at an energy that is 2 times V shifted with respect to the transition energy of a single molecule. And the state is simply a coherent sum of all the states n without any phase factors. If you look at an arrangement like this, so that all the molecules are pointing in the same direction, then one sees that the interaction becomes negative. So this state that carries the complete absorption strength is located at the bottom of this exciton band. And it will have a very strong absorption strength and also a very strong emission strength. So this state will be redshifted with respect to the single molecule absorption, and its radiative decay will be enhanced by a factor n with respect to a single molecule. And this is typically referred to as superradiance. In the other case, when the molecules are arranged like this, so the dipoles are still parallel, but perpendicular to the connection vector, then you see that the interaction is positive. So absorption takes place blue shifted with respect to the single molecule case. After this absorption, there's a thermal relaxation. You relax down to this state, and this state is a dark state. It does not carry any transition strength, so you will decay non-radiatively here, and there's no emission. And in the general case, you can have essentially anything. You have a complicated band structure and many allowed transitions. But you see that in principle, you can roughly understand why you can have a red-shifted peak with strong emission or a blue-shifted peak with no emission. And so one sees that by changing the geometry, one can qualitatively change the optical properties. And so typically for these aggregates in solution, the geometry is not known. And one would, from such spectra, get conclusions how they are arranged. But one has to be very, very careful, and there are many pitfalls. And that is that this purely electronic theory that I have presented is not sufficient. And one would get, for example, one would say, oh, these peaks here, they would be electronic transitions, but in fact, they are of vibronic origin. So to make correct conclusions, one must include vibrations. And vibrations, unfortunately, make the problem hard. And I will just say a few words, because that is what we spend most time on. So we have developed and used very different theoretical approaches, for example, based on green operators or diagonalization in a large vibronic basis, then surface hopping, and my favorite are the stochastic Schrödinger equations. And each of these approaches is appropriate for a specific situation. For example, the diagonalization in a vibronic basis is typically good when you have a small number of molecules and you only care about a few vibrational modes. Then you can model each molecule not only by two electronic states, but actually you describe them by two Oppenheimer surfaces. You can, for a single molecule, get this vibrational progression, which you convolute by some disorder. And from that, you can then calculate for the dimer how the spectrum looks like. And this works rather well for small systems, so in particular for dimers. When you have large systems, typically approaches based on green functions are good, but unfortunately, so this works really well for large systems. You see the agreement with experiment and theory is very well. But unfortunately, this approach did not work for transport, and also it was not good for emission. Therefore, we tried the stochastic Schrödinger equation approach, and I will not say a lot, but I will just say that it works in most situations. And unfortunately, also, if you have a large number of molecules and many vibrations, this is still problematic. But you can handle environments very well. And just to give you an example, so when you have this monomer spectrum, and let's say an arrangement like this, and you increase the number of molecules, then you see that here this narrow peak emerges in absorption, and here you see a broad blue shifted spectrum appears. So this is all covered very nicely in the stochastic approach. And so before I now come to the experiments and the actual findings, let me make a final remark about theoretical methods. So to my experience, all methods have typically problems for large systems and many resolved vibrational modes. And also, if you have strong light-matter interaction, it becomes difficult, because then you need additional states with higher excitations, and your Hilbert space grows very, very quickly. Okay, now let's discuss molecules on a surface. And our general interest here is how this collective excitations, so this delocalized, coherently delocalized states, how they affect the radiative and the non-radiative processes. So, for example, single fission, exciton-exciton annihilation, and superradiance, on which I will focus. And we studied, for example, molecules that are randomly arranged on noble gas clusters, or molecules that are on dielectric surfaces. And here you have an ordered arrangement. In both setups, they have nice properties and some not so nice ones. And in the following, I will focus on this system here and give you some details about experimental findings and our interpretation. So this system here, you see an AFM image, unfortunately not from my collaborators and not from the samples where I later show results. But you see here, this is roughly how the arrangement looks on a large scale. And if you zoom in, you see here individual PDCDA molecules on this potassium chloride surface. And this was done with an atomic force microscope. So you see, they are nicely arranged in a so-called brick stone arrangement. And this we will now also see in our samples. And the experiments that I will discuss are done by the group of Professor Sokolowski in Bonn. And our main question was, how can we achieve an enhancement of the radiative decay rate in these systems? So what properties do we have to fulfill? And when I mean radiative enhancement of this radiative decay rate, what I mean is that the ratio between the decay rate, the radiative decay rate of the aggregate with respect to the radiative decay rate of individual molecules becomes large. So I will use this eta for this ratio. And the nice thing is, if you have such an increase of the radiative decay rate, that leads typically also to an increase in the fluorescence quantum yield, and you can have a brighter emission of such devices. In our experiments, we did not have an AFM, but we can get information about the arrangement from low energy electron diffraction. And from this, we know that we have finite size domains. So they have roughly the size of 10 × 10 molecules. And this size depends on the preparation conditions. I will discuss two samples that are prepared differently later. And we also know that we actually have a broad distribution of sizes. And we had two different samples, and there the domain size differed by a factor 2 and 4. So they were prepared differently. So let's take a first look how optical spectra look like. And what I show now, it's done in ultra-high vacuum via evaporation epitaxy of these molecules on a potassium chloride surface. And the spectra are recorded via detecting fluorescence clicks. That's why we also use a dielectric function, because then we see fluorescence. When we look, so we can put a very small number of molecules on the surface and then look how the absorption and emission spectra look like. And what you see here, that's under this situation when there are essentially individual molecules on the surface. The red is what I call absorption, and the black one is the corresponding emission. And what you see here, these peaks, they all belong to certain vibrational modes of the molecule. For example, this peak is an overall breathing mode of the molecule. And this high peak, that is if no vibration is excited, that's the so-called 0-0 transition. And again, we see for the monomer, we have a mirror image in the emission. And one can also look at these ratios of these peaks, and one sees that, again, to a very good approximation, we have harmonic or non surfaces in the excited state and the ground state. If we now go to the sample where we have type of monolayer, then we have a strong change, we have a redshift, and the vibrations are gone, as it was in the case of this J-bands, J-aggregates that I discussed before. So there's a little bit vibrations left here, but emission only has a single peak and no excitations of vibrations. Okay, so this is a candidate for this case of the strong emission and superradiance. And indeed, when we measure the fluorescence decay rate, then we see that for this sample, it's enhanced by a factor of eta, roughly 22, with respect to that of a single molecule. We can also check how this enhancement is affected by temperature. So if you increase the temperature, you expect that you destroy this coherent superposition state. So, and that's indeed what we see with increasing temperature, this enhancement, the fluorescence rate that goes down, and it goes down roughly like 1 over temperature. Okay, we can now try to do calculations. And what we know is, of course, for an individual molecule, the transition dipole, or the transition density, if we want to make very accurate calculations. We know the arrangement, and with that, we can immediately calculate the interactions. So some of them are negative, and some of them positive. Now, of course, we have many vibrations in the problem. And as I emphasized before, vibrational modes and many molecules in general make the problem essentially unsolvable. However, for the present case, the parameters are luckily such that one can do perturbation theory in this dipole-dipole interaction. And what one then finds for emission, that one does not have to include explicitly vibrational excitations in this one exciton subspace, and one can treat really the effect of the vibrations purely perturbatively, and one sees that this results in a rescaling of the interaction. And here in this case, it's roughly a factor of 1/2. So interaction becomes a factor 1/2 weaker than if you would not include vibrations. Okay, now with this, we can calculate the emission of individual states, and then we can calculate also an enhancement factor. And the way we do this is now initially, we are in this manifold with one excitation. We have calculated the eigenstates by diagonalizing the Hamiltonian with this rescaled interaction. And we then can calculate the transition strength for each individual eigenstate. And for parallel molecules that we have here, we see that these expansion factors, they determine this transition strength. And if we have a fast thermalization here, then actually one can calculate an overall emission rate. So this is the eta in which we're interested in, via taking for each individual state the corresponding transition strength and weighting by the population of this state that depends on temperature. So the PLs here are Boltzmann. So that indicates that each state is populated according to a Boltzmann distribution. This then gives the enhancement of the emission for the coupled system. Okay, the first thing is we checked that actually the assumption that we can ignore vibrations is okay. And we looked, so vibrations in the excited state. So we looked now at emission spectra, and what you see here in blue is an experimental curve, in red is the theoretical calculation. And so this is this emission peak, and this is actually a zoom into this yellowish region here. So there are some vibrational contributions, but they are very, very tiny. And okay, indeed, we can reproduce them, and that shows that the theory seems to be okay. And this was done for a 10x10 domain, which is roughly what we expect for this sample. And for similar domain sizes, we actually get similar agreement. But when the domain size is either very small or very large, it looks completely wrong. Okay, so this already shows that things are fine. And we also looked at absorption spectrum and looked how that changes, and that also is okay. Then we looked at the radiative decay rate. And as I said, we had two samples. This is the sample with the small domain size, and we simply calculated with this very simple approach of the previous slides how the enhancement changes when you increase the temperature. And here you see the result for 10x10 domain, and it very nicely fits to the experimental curves. These are the black dots. And again, if you have slightly different domain sizes, the curve looks also good, and the agreement is similar. Now, we had the second sample where we had a better preparation condition and we had larger domain sizes. And for this sample, we measured these black curves and the black dots. And the first thing you see, we now have an enhancement that is up to 50. And so this is partly due to the fact that here we only could go to 20 Kelvin, here we could go roughly to 10. But what you also see is that when we decreased the temperature more, there's a drop. So we do not grow as we would have expected, because we thought at 0 temperature we should be up here somewhere. And then we started to do our numerical calculations. And for example, for 40x18 domain, that's here the blue curve, we also see that when we go to low temperatures, actually we have a decrease in the enhancement. That's completely opposite to what we expected. And actually, we find that many domain sizes give similar agreement. The only important thing is that the domains must be strongly asymmetric. So one side must be roughly 2 times longer than the other. Then we also looked again at the LEED, and indeed, there also we can see that we have a lot of elongated domains in our sample. And if we average over a domain distribution that we believe represents roughly our domains, then we really get this black curve for the sample with the large domain sizes, and here the red curve for the sample with the small domain sizes. This agrees rather well. And here you also see much better how this drop starts for these large domains. So what is the origin of this drop? We were wondering. And when one looks now at the eigenstates and the transition strength, one can actually easily see why this is happening. So here you see the 10x10 domain, and what I show here are the locations of the eigenstates, so the eigenenergies. Each black and each white dot are an eigenenergy, and these sticks, they show you how much transition strength each energy has. So for this 10x10 domain, the energetically lowest state has the largest transition energy. Then there's a state that has no transition, and so forth. But for this elongated domain, the states at the band bottom, they actually are dark. So they cannot absorb and also not emit. And that's the reason why at low temperature here, no excitation, no emission will occur, and only when you increase the temperature, this becomes populated, and then starts the emission, but very strongly then. And if you look at the corresponding wave function, this wave function here is nicely symmetric. This has a nodal line, and it's the ground state of this one exciton manifold. And yeah, here you see again the corresponding curves. This goes really completely to zero. This is a complete dark state. Okay, the main messages from this is for the samples with the larger domains, at low temperature, there's a decrease of the enhancement with increasing temperature. We expect it to go up here up to 75. And so we could trace this back to a dark state at the bottom of the band that appears for these elongated domains. And so the main message is to obtain large radiative enhancements, as we would like to have. One should not only increase the number of the molecules within the domain, what we thought, but one should also try to keep the domains as square-shaped as possible. Otherwise, you run in this problem with the dark states at low temperature. And so the states at the bottom of the exciton band, they can actually well approximated by this formula. And really these states here, they can be very well approximated by this simple, purely electronic form. So, and now we would like to directly measure these wave functions. So measuring these wave functions means essentially measuring these coefficients. And our idea was to use near-field spectroscopy for this. So to access this, in far-field spectroscopy, this absorption strength of the eigenstate L is essentially given by the formula where the electric field is constant over the complete sample. Then you can move it out, and only these coefficients and the dipoles play a role. And this resulted in these selection rules with the dark states. So if you want to access, for example, this dark state, you have to break the selection rules. This you can also do via this near-field spectroscopy. And the idea of this near-field spectroscopy is that the field, so the electromagnetic field that you use for the excitation, that changes over the length scale of a few molecules. That is sufficient to break here selection rules. So I indicate this by this dependence on the position of the molecules. And there are many ways how one can create such near fields. For example, with typical scanning, near field optical microscopy, where you shine in a laser on a metallic tip, and then you look at the scattered light. Or you can use the setup that the Raschke group has developed, where you couple light into such a tip. Then you create a localized surface plasmon that has the nice effect that you don't have light that shines directly on your sample. And now these tips have the additional benefit that you can scan the tip position over the structure, and at each position you can in principle record a spectrum. So with X tip, I mean the position of this tip. And in the following, I show theoretical calculations where we place a tip roughly 1 nanometer above the surface. And since we cannot really model such a complicated tip, we approximate it by a metallic sphere. And I will show you results that really come only from this simple formula where we ignore the presence of the tip at all, but we have confirmed and or validated the simple calculations by doing a self-consistent field approach with coupled dipoles, where we model the tip in more detail via a polarizability tensor, and then calculate really the scattering from such an arrangement. And this gives essentially the same results for the parameters used in the calculation. And these parameters are, we take a rather small tip with a diameter of 5 nanometer, the tip molecular distance 1 nanometer, and for what I show now, the oscillation, so the emitting field from the tip is polarized perpendicular to the surface. So we also investigated other polarizations. And what you see, so I show here the result for 10 cross 30 domain, where we place the tip at 9 different positions, and in each position we get a spectrum. So this is frequency, and these are the absorption strength at these different positions. And as a comparison, here is the corresponding far-field spectrum. And what you see, indeed, many states become accessible. And in fact, all states now carry absorption strength. And in particular, the states at the band bottom that would be usually dark now also can be excited. So this state we can access. So now, of course, two questions emerge. Can one somehow understand these spectra, and can one use them? And in particular, can we learn something about these wave functions? And to this end, it's not good for you. Sorry. So to understand something about these wave functions, what you can do, you can now scan with the tip at a fixed, and look how at a fixed energy the absorption changes. So for example, you go to the energy of this lowest state, and then you look how does this change when you change the tip position. This you can do as a function of position. And on the next slide, what you see is for the example of a one-dimensional chain where we scan the x position. So this is for the state with the lowest energy. This is for a state that is in the middle of the band, and this is for a state that is at the top of the band. So we see here some variation of the corresponding absorption strength at that energy. And now the question is, can we obtain from such scans these absorption, these expansion coefficients? And the short answer is yes, we can. And we have done this by training a neural network to invert this to the corresponding wave functions. And the nice thing about these neural networks is that they also work when you would have very noisy measurements, as clearly, if somebody would ever do this, there would be a lot of noise. And for example, you see, these are these position-dependent scans without noise. And here, if we add random noise on these measurements, we still can perfectly predict the underlying wave function. And for example, it's surprising, for example, for this state, where really a lot of noise is disturbing the things, but the wave function coefficients are nearly perfect. And also for two-dimensional systems, this reconstruction of the wave function works rather well. Okay, let me summarize. I have discussed molecular aggregates, and I hope I could show you a little bit that they are interesting systems with various applications, and their properties are based on these extended coherently delocalized states. And I wanted to emphasize that theoretical methods in general must be able to handle coupling in nuclear degrees of freedom in a non-adiabatic and non-perturbated manner. And these aggregates on dielectric surface, they are very clean systems where you really can do rather precise measurements and precise calculations. And using near fields would give access to optically forbidden states, and one would be able to really map out the wave function coefficients from scans of the position. And probably even if there's noise and disorder, this will work. And the next thing we find rather interesting, if one combines now with femtosecond near-field spectroscopy, then one could really follow how does excitation decay. Another topic that I think is interesting is really to couple molecular transitions directly to the plasmon resonance of the tip. And you would have to make the tip a little bit larger or closer to the surface. Then you would also break selection rules for emission. And yeah, this is, for example, necessary when you have aggregates that do not show fluorescence. Yeah, and yeah, this would be essentially a general context when one couples these aggregates to nanoparticles. What can one tune? And then the last thing would be combine the effect of charge and excitation transfer. So you could think not to optically excite the molecules, but exciting via a tunnel current, and then you can look how does the system respond. And actually, there are groups starting to do this now. And yeah, and with this, I will acknowledge certain collaborators, in particular here. This was done by Moritz Sokolowski in Bonn. And I thank you for your for listening.